Thank you, Norbert. So it's a very pleasure to be here with you and to participate in the workshop last week, and also to introduce a recent work that I did with my supervisor on Nikita. It's about quantum foundations, and to understand more precisely, so the incompatibility of quantum measurements. Incompatibility, and on one hand, and on the other hand, so non-locality or Bell violation. And are these two notions, are they equivalent or not? In the sense that if you observe a violation of a Bell inequality, is it necessary to have incompatible measurements, or having incompatible measurements, is it equivalent to non-locality, to observing a Bell violation? And we will see later on that these two notions can be related and understood in the framework of tensor norms that I will introduce later on. But before, so I will start with the very basic. So let's take how we can understand the Bell inequalities. So you can have some two person, Alice and Bob. They will receive space-like separated, and they will receive some input x, and Bob will receive some input y, and Alice will give some output a, and also Bob will give some output b, and they will share some probability distribution between them, and they will calculate some quantity. And so before x and y are taken just 0 and 1, and a and b, so also 0 and 1. And they will calculate a quantity, the expectation value of observing a for a given sorry.
Sorry. No.
Oh, okay, sorry. So they will calculate this quantity. So for a given input zeros, and the expectation value of observing the output a for a given input 0, and also the expected for a given input y, Bob will give some output b plus a0 b1 plus a1 b0 minus a1 b1. And with ax by is given as sum over all Alice and Bob output with probability of having the output a and b for a given input x and y. And they can use either classical or quantum. So
shouldn't a and b be plus minus 1? I'm assuming this is CHSH.
Sorry?
Assuming this is CHSH.
Yeah, this
shouldn't
is
a and b
CHSH.
be plus and minus 1 instead of 0 and 1?
It can be plus or minus 1 or 0 and 1. So it's Z2.
Yeah, this the CHSH one is different.
Oh, okay, yeah. So, and the shared probability, if it is classical, so for classical, in the classical setting, so the shared probability, it's factorized with some hidden variable of the probability of Alice answering A for a given question X, and the hidden variable lambda, and Bob probability of answering B for a given question, for a given input Y, and this hidden variable lambda. And if they use quantum, so they will compute this quantity. So they will share an entangled state, and Alice will perform a measurement over some Pauli, let's say some Pauli measure. And if Alice receives the input I, so she will measure in the direction in a direction EI, and with the in the orthogonal basis. And if Bob receives some input 0, so he will measure on the vector 1 plus 2 over square root of 2, and for y equals to 1, so, or plus 1, sorry, minus 1, so he will measure over E1 minus E2 over square root of 2. And if you use classical, so you can see that, so if you use classical, you can see that this quantity can be bounded by 2, but if you use quantum, so for quantum case, this quantity attains to square root of 2, which is strictly larger than 2, and this quantity I will write it for later on. So I will write this quantity as all what it is here. So I will write it as the sum over xy, gxy, ax, by with j. It's the CHSH matrix 1 minus 1. Okay, and the value 2, I will call it beta of j of CHSH, that will come later on. And to square root of 2, I will call it this quantity, I will call it beta star of GCHSH. Now it's just notations, but we will see later why. Okay, and now, so this is a way to introduce a Bell inequality violation and how we can understand them in a natural framework. So there is a framework known as non-local games. So what is a non-local game? So we have we have Alice and Bob, baseline separated, and we have the referee. And the referee will start asking a couple of questions to Alice and a couple of questions to Bob. So you will ask X to Alice, Y to Bob, and Alice should give some input, some output, sorry, A, and some output. Alice and Bob are space-like separated, they are not allowed to communicate. And all the game, I will call it J, is characterized by the set of Alice that the referee will ask to Alice, the set of the same also the questions that the referee will ask to Bob. Alice, the set of Alice answers, the set of Bob's answers, and some probability of the referee choosing the question X to Alice and Y to Bob, and some payoff. With by the probability, so it takes values from the Alice questions and Bob's question to 0, 1, and this payoff V is given by takes values A, B to 0, 1, J, X, Y, A, B. Okay. So this is what we call the non-local game, and the thing is that they should calculate in this setting. Alice and Bob, they should calculate a quantity. I will call it omega GP, and this quantity it's given by the sum over all Alice and Bob, the Alice and Bob questions, and all the sum over all Alice and Bob's answers of the probability of the referee give the questions X and Y to Alice and to Bob times this payoff times the probability of Alice and Bob answering A and B for a given question X and Y. So they should calculate this quantity, and this quantity characterize somehow if the referee agrees on Alice and Bob answer that they will give later on during the game. And I think they should optimize, so they should optimize over, they will use again classical strategies or quantum strategies, and they will optimize over this those strategies. So what we call the classical value of the game J is given as the omega of J defined as the supremum over all shared probabilities, classical of this omega and quantum is the same quantity, but now we optimize over all quantum probability distribution shared. Okay, now what is the set C and the set Q? So the set C is defined as all the possible probabilities that factorize, like in the case of CHSH. Over some hidden variable, the probability of Alice answering A for a given question X, and the hidden variable lambda, and the probability of Bob answering B for a given question Y. And the quantum set is defined as the same probability of Alice and Bob answering A and B for a given question X and Y, such that it will be written like with the tensor product with the for a given question X, Alice should measure over on the POVM AXA and also the POVM BYV with the AX. Those are POVMs, so those are positive. And if you sum over all Alice answers, so it's equal to the identity. And also for Bob. So also for Bob. And another class of games which are very interesting, known as XOR games. So those XOR games are defined as so it's the same as a non-local game, but now the Alice and Bob output are just plus or minus 1. Or is it true? And in this game, and the payoff that I didn't specify, is given as 1/2, 1 plus minus 1 of Alice with the XOR with f, it's a function from x, y to 0, 1, x value 1 to 0, 1. So this is how we define this type of XOR games. And if we replace the payoff in the setting of in the formulas above. So what we'll obtain? So we'll obtain something which is analogous to this classical value of the game and the quantum value of the game, known as the classical bias or bias. Let me define the bias. So the bias, it will be given by J and gamma. I will define it later over xy xy, gamma xy. And what is the relation between these two? So if you compute this, so you will find that beta of j and gamma is given by 2 omega t minus 1. And this matrix here, j, xy.
Sorry, what is gamma?
I will define it.
Okay.
I will define it, yes. So, and gxy, it's given by the probability of having the quotient x, that the referee will send the quotient x and y, times minus 1 to the power of xy. And now what is gamma? So, gamma, I will call it correlations. Correlations. And those correlations can be classical or quantum. So if there are classical, or I will call it local, I already used the letter C. So the correlations, the local correlations or classical correlations, gamma xy, are defined as all the possible gamma xy such that they are distributed with some probable measure of ax lambda times by lambda. And what is this ax lambda and by lambda? To make the link between what you have seen before. So ax lambda is the probability of Alice answering 0 or plus 1 for a given question x and the hidden variable lambda minus the probability of answering minus 1 given question x and the hidden variable lambda. So this, and also for Bob. And the quantum correlations, Q tilde, I will define as gamma xy. Yeah, but now gamma xy are defined by some shared quantum state a of x tensor by. And a of x here are very particular in the sense that we have just in the are very particular in the sense that here we have just two outcomes, just plus or minus 1. So this set a of x is given by the first POVM and the POVM, the element of the POVM are given by, and those are the Alice POVM, ax and ax minus 1. So they sum up to the identity and they are positive. So those are the, and this is the measurement apparatus. Those are the POVMs.
Okay, so it's not that A must have eigenvalues plus minus 1.
Sorry?
It's not necessary that A has eigenvalues plus minus 1.
No, not necessarily. Okay, so this is the classical correlation, which is analogous to this quantum correlation set, and also to quantum probability distribution, the set of all the quantum probability distribution, and also for the classical one.
So sorry again, so this is beta, which is the sum over G times gamma. That's what? That's a maximum you can obtain with a strategy from the corresponding set of correlation gammas?
It's not the maximum, but it is analogous to omega GP that I defined here.
What was omega GP again?
So this is the whether the referee will agree or not on Alice and Bob's answer. This one.
Right.
This one.
But now there is I see. Okay.
And now as before, so this bias, I can define the classical bias and the quantum bias. And the classical bias is the optimization over all classical correlations, and the quantum bias is the optimization over all quantum correlations, which is analogous to that I defined before. So, well, here. Okay. So the classical bias. So it's given by. Now you take the optimization over all gamma in the local set L, and the quantum bias. Optimization over all quantum correlation set. Q2. Yes. Okay. So this is how we can understand formally the Bell inequalities in the setting of non-local games. And now it turns out that those type of non-local games have some nice mathematical properties related to tensor norms. So I will give a brief introduction to tensor norms, and I will introduce just what is necessary for my talk. So I will go here. So what is tensor norms? What are tensor norms? So intuitively, so you have tensor, and you will put a norm on this tensor. But formally, what is it? So you take a Banach space, a finite dimensional Banach space. You will take two finite dimensional Banach spaces, and you want to construct the tensor product of two spaces. But you ask which type of norm I will put on the tensor product structure of these two Banach spaces. And it turns out that there exist two interesting norms, what we call the injective norm, defined for a given Z, tensor Z in tensor product of X and Y. Define the injective norm. I will note it by epsilon. It's defined as the supremum over of alpha tensor beta on Z, on the tensor Z, as a function or not. There is no scalar product structure here. There is just a function, a linear function acting on Z. And the space and the alpha, it's in the dual space of a unit ball of the dual space of X. So we define a dual norm of that, and I will denote it by XR. So it's a dual a unit ball in the dual space, and also for beta. So this is the injective norm, and there is another interesting norm known as projective norm for a given tensor. You define this projective norm as the infimum or the minimum, the infimum over all possible decomposition of your tensor as sum of rank 1 tensors of the quantity sum over A, the norm of X on X, and the norm of Y on Y. This is how we define the projective tensor norm. And what is the definition of a tensor norm? A tensor norm, I will those are definitions. So we say, no. So a tensor norm now I will denote it by, you can construct it on the tensor product of x and y, and I will denote it by some alpha here. And this norm is, you define that you define a norm on the tensor product of these two spaces, and a tensor norms, or a tensor norm, it's something, it should lie between the projective tensor norm and the injective tensor norm. So you take a tensor product of your vector space, you define a norm on it, and if this norm is in between the injective tensor norm and the projective tensor norms, you define it is a tensor norm. And something, if you take a tensor of rank 1, in tensor of rank 1, it's factorized in the sense that if you take Z written as U tensor V, and you can show that if you take the injective norm of Z, it will be equal the injective norm, the projective norm, sorry, of R. And also, if you have this tensor norm, also it will be equal to this tensor norm alpha, and this it will be given by the norm of U living on the space X times the. So rank 1 tensors factorized in this sense. Something how what okay. Alright. So we have this definition of a tensor norm. I want to say something. Okay, yeah. As an examples, so to make it more concrete, so you can show that if you take a banach as a vector space endowed with the L2 norm, injective norm with L2, it is the same as a matrix of dimension n endowed with the space of all matrix dimension n endowed with the matrix with the norm, the natural norm that you put on the matrix, and if you take the projective norm, so you have the same matrices of dimension n, and now with the one norm on the matrix, which is defined by trace of absolute value. We have these examples, and why I discussed why I'm introducing tensor norms. It turns out that due to a famous theorem by CHSH, so if that shows that there exists a correspondence between the classical bias and the quantum bias, and related to this framework of tensor norms. So CHSH theorem says that if you try to calculate, if you calculate the classical value of the gain, you can show that this is equal to the norm of J of the game in I always call it in L1, yes. In L1 space, Tensor injective norm of L1. And all the entries of those matrices are real. So if you see the matrix or the game J as a matrix and you see it as a true tensor, so you can show that the classical value of the game is equal to this injective norm of your true tensor. And if you compute the classical, the quantum bias, which is given as the norm of J on the same space, but with another norm, I will call it gamma 2 star norm, which is not important to define it here, but which is a reasonable, it's a tensor norm in this definition. So this is gamma 2 norm, so it satisfies this property. So I will not show it, but and this is what he showed. And the thing what is beautiful in this setting is that all what you need to know, if it is classical or it is quantum, can be completely encoded in some sense on the geometry of the Banach space itself, on the norm of your game that you define.
Is it an intuitive way to see why this holds for the epsilon norm?
So this one it's intuitively, it's because you have just answer plus or minus 1. So we'll have some L1, some L infinity that will appear somewhere, and when you take by duality, because of the injective norm, you take the supremum over the dual space, L1 spaces will appear.
And why the epsilon norm?
Oh, why the epsilon? Because, where is it? Because when we will have, actually we will have a J, okay, so we will have sum over xy, gxy, ax, and by, taken plus and minus 1 values, okay, and those are J, A, B, and you have this structure of a functional application on J, and A and B are living in the unit ball of L infinity. And by duality, we have an L1 space and an L1 space with an injective norm here.
What is capital N, actually?
Sorry?
Capital N in this.
Oh, capital N is that? Oh, it's oh, sorry, I didn't. It's the number of questions that the referee will ask to Alice and Bob.
What is G? Sorry, the matrix you wrote there, no? G, X, Y.
Sorry?
The G you're writing there for the norm?
The J here, yeah, it's the GXY.
G.
That one. That I defined, but it's.
This is also then on sequences of questions.
Sorry? GXY?
Yes.
No, you fix the game.
Oh, no, it's a deterministic list of
Yes.
questions. Okay.
So you take a game,
Yes.
so, and the game is completely, as I said before, so it's given by the probability of Alice, the probability of referee will give questions to Alice and Bob, times minus 1, some function that will take 0 and 1, and this is completely fixed, and all the players in this setting know what is this J. Okay. Yes, so this is GXY, yeah. The matrix that will characterize, that will encode the game itself. Okay, so now, so this was the first part. Now, what we want to do is to understand incompatibility and non-locality in this framework. But before, let me say what is compatibility. So, compatibility that two POVNs are compatible if there exists another third POVN CHG such that the two are marginal from this POVN. This is the definition of compatibility. And now how we can relate this compatibility framework with non-locality in the system of non-local games. It was shown before, so the motivation is that they, in a paper by David Perez Garcia, I think also Misha Wolf, Carlos Fernandez, I think. That compatibility is equivalent to Bell violation or Bell inequality violation. So Bell, we call just Bell violation. In the setting of where J, the game, is given by the CHSH game. That I recall is just plus and minus 1 matrix. And how about more general game? So the question is that how about more general? Is it true that we have the equivalence between these two notions? What is sure that if you have a Bell inequality violation, for sure you are incompatible. But what is not sure, what is not known, whether if incompatibility implies a violation of a Bell inequality. This is our result. So now I will introduce our framework. So to answer this question, we will use the framework of non-local games, but we will modify it a little bit. And we will see what. So now incompatibility. Okay. Incompatibility versus Bell inequality. Again, now the referee will play a game with Alice and Bob, space-like separated. So he will ask a couple of questions to Alice, a couple of questions to Bob, and Alice should give some answer A and Bob give some answer B. And the difference between the other setting is that now Alice may have more than all her measurements are completely fixed. And they may or may be not compatible. And she wants to know if she is incompatible or not. Is she violating a Bell inequality or not? So she will fix all her measurement apparatus. And here the game again is Alice and Bob. Alice and Bob answer are just plus and minus 1. And the number of questions that the referee sent, so n questions, and the game again is characterized by this matrix Gx1. And in this setting, she wants to know that if she observes if she has some incompatible measurement, then she will observe a Bell violation, and how we can formalize this.
So before the question was basically given that just a matrix G, so the rules of the game, I want to optimize over all probability distributions, which means optimize over quantum states, basically, and the A's and the B's.
Yes, exactly.
So now you fix the A's, but you still optimize over all the B's and the quantum states? Is that the question?
Yes, so the thing is that now, in this framework, so we fix the A's, and you optimize our both measurements, you optimize our all shared quantum state, and let's see what will happen. So, she will construct, so Alice now, she will construct a tensor. Alice will construct a tensor A, and leave it in Rn tensor MD, and she will compute a quantity that will characterize the compatibility. But instead of having this algebraic formulation of compatibility, I will give a new formulation with norms, or with tensor norms. So, compatibility. So if she wants to know whether her measurements are compatible or not, so she will construct a tensor, and she will compute a norm of this tensor. We call it AC. And this norm is defined as a thema of possible decomposition of A of this form, with ZG, it's a vector living in the unit ball in infinity, and HG are positive semi-definite matrices. And what is the quantity that she should minimize? So it's the sum over all the positive matrices in the natural norm. And this is the compatibility norm. And the first theorem, a theorem that tells you that if this norm is less than 1, is equivalent to compatibility. So, well, she constructs a tensor, and she will find over all possible decomposition of this tensor with some vector living in the unit ball of n infinity, and with positive definite matrices of this quantity here. And if this compatibility norm is less than or equal to 1, means that all her measurements that she used are compatible.
Is there an easy way to see, at least intuitively, why this?
Intuitively, I would say, so somehow this AG, A of G, it will be described by, it will be given by this matrix that will make everything compatible in all Alice measurements. And since it is a P of M, it sums to 1, the identity, and with the ephemeron, the compatibility is less than or equal to 1.
What is the tensor that he has to use. Like if I give you, how do you construct the tensor from the PLVM elements?
Oh, yeah. So she can construct, for example, a tensor that she can construct is given by sum of x, some vector, tensor, her measurement apparatus. And she will look at, you don't have a unique tensor, tensors are not defined uniquely. So she will look at as a possible decomposition of this form that will minimize this quantity here. Yes?
B doesn't play any role here?
Oh, B, so we will see later. So B, we will not care about it, so much about what Bob will do, because we will optimize over all his measurements, and later on also over all the quantum state that they will share actually. So now Alice, her measurements are fixed. She calculates this compatibility norm, and if this compatibility norm is less than 1, means that all her measurements are compatible. Now how about non-locality? So, and this is where Bob's measurements actually, she will optimize our all Bob measurements, and we will have this definition that Alice measurements, Alice, the definition, are J, Alice measurements are J local, Bell local, if A of J is less than or equal beta of J. And what is this A of J? A of J is given by the supremum over all Bob measurements and over all shared quantum state of the sum Gxy psi A of x tensor Vy psi. In another sense, so she will say to Bob, okay, let's calculate this quantity, and Bob, optimize over all what you want, over all the measurement apparatus, and over all the shared quantum state. And if you cannot do better than the classical value of the gain or the classical bias, it means that you are local. It means that Alice will not see any Bell violation inequality. So this is the definition of G Bell local. And now something that I will you can show. So I will not. It's technical, but it's not very important. You can show that these two norms that I defined here are tensor norms in the sense that I defined before. So A of G and A of C, you can show that is less than the projective norm and are greater than the injective norm. You can show that those are tensor norms. I won't show that. So it's technical. But so now what we have, so we have a quantity that will characterize Alice measurements, whether if they are compatible or not. And now we have this norm that will characterize if Alice measurements or if Alice see any Bell violation or not. So now all what she will do, she will compare these two norms. And why she will compare, she wants to compare these two norms? Because if if I traduce what this paper says in our framework, it says that the norm A of J in the CHSH game is equal to this compatibility norm. So this is why we want to search whether these two norms are equal. So in a equivalently, we can say that do we have what are the J's?
The classical CHSH bound beta is 1 in this case, or?
Exactly.
Okay.
Exactly. The classical bias is equal to 1. And now for any G, so we want to know whether we have this equality between these two norms. Means that you need to show that A of G less than A of C, compatibility norm, and also and we will see later that if you want this, the game itself should satisfy some property. And this is what the question we will answer. So, and the answer to this question is the first main theorem. So main result. So the first theorem that we have, that if you calculate A of J, you can show that it's less or equal the compatibility norm times the classical bias. And this first result, you see immediately if Alice measurements are compatible. If Alice measurements are compatible, so it means that this quantity is less than 1, which implies that A of J is less than the classical bias. It means that she is effectively J-Bell local. And the second theorem, it depends on how much time do I have to give the proofs. Okay, I will see later.
People, but I think we should not go much above an hour, probably.
Okay, sure. So
If people want to know it, they can stay afterwards.
okay, sure. So and the second theorem, it tells you that the compatibility norm is less than or equal this norm times how to write, so times I will write it like the maximum inverse absolute value. Okay, so inverse absolute value J. And in this setting, I assume that also J, the game itself, is invertible. I'm assuming J is invertible. Why? Because it's hidden actually. Where it's hidden there to prove that A of J is a norm actually. So and this is why we need the invertibility of J. And you see from these two theorems that if you want the equality between these two norms, so by theorem 1 and theorem 2, so I will erase this here. So by the first theorem and the second theorem, you see that immediately that this, if we want that A of J equals A of C, this will imply that the classical bias times this maximal inverse of the matrix is greater than or equal to 1. So it is kind of, I will not say that, but it's, I will say, but it is kind of uncertainty principle somehow on the game itself, in the sense that this comes from quantum and this is classical somehow. So the game itself should satisfy this inequality.
Equal than 1?
Sorry?
Why larger or equal than 1? I'm a bit confused.
Oh, so it's just you multiply these two.
Am I missing something?
No, sorry, it's not. Oh, sorry. It's not. It's directly from. It's not because you want this. Because just from theorem 1 and theorem 2,
It has to be.
you have this thing here that appears.
Yeah, exactly. So that's not what you want. That's what anyway. Get.
Yeah, sorry.
Then that makes sense. But you want the opposite, no? Because as far as I see, the problem is that you say, well, my measurements are incompatible. I would like to see that this gives some kind of Bell violation, right? So you have a big AC norm, and you want to infer that the AG norm is also big. But then the maximum shouldn't be too big, because if the maximum is very big, you will not get out anything for G, right? Anything useful. So that's right. And you want that this is not too ill-conditioned, I guess. Too.
Well, in the sense that for the CHSH game, so from theorem 1 and theorem 2, you have this is naturally, yes. But if you want to restrict in the case of, like, in this sense, so what you will have, so what you need to show, what you need to show that the game, that the classical bias, if you want classical bias equals to 1 and also this maximal inverse equals to 1, like the CHSH game. So you need to see what type of games J that gives you, that satisfies this following equality. And you see from theorem 1, theorem 2, we have this. And from here, you want to see where we can, when we can see the equality, where the equality holds with 1.
I'm a bit confused again. The beta for the CHSH game is what?
Sorry?
The beta for the CHSH game is what?
It's
1 or 2? 1? Because the G inverse is 1/2 times the G matrix, right? So the maximum is 1/2. And then this equality is not 2.
Someone have something?
I mean, the inverse of the G matrix, as you wrote it, was 1, 1, 1 minus 1 is 1/2, 1/2, 1/2 minus 1/2.
Yes, there is a, maybe I missed some.
In the beginning, you said that beta G was equal to 2.
I remember.
In your first board, you said it was equal to 2. When things were normalized, it was equal to 2.
Yeah. Okay, yeah, sure. Okay, I need to define the CHSH with normalizing with 1/2. Yes.
Okay, so when you write this equals to 1, it means that CHSH should actually have exactly that property.
Yeah, exactly.
That was my
And now, which type of matrices satisfy this equality? So the last theorem, and I will find, I think. So the last theorem, we can show that in general, you have so those are J matrix of dimension n, square n by n matrices. So in general, you can show that beta of J time times the maximum greater than or equal square root of n over 2 greater than 1 for n greater than or equal to 2. And if n is strictly larger than 3, then you will not have equality with 1. So you will have. It means that you should restrict the dimension to 2 if you want to saturate this inequality. And when you do so, you can show that for n equals to 2, the only matrices that gives you this equality here, so I will equality. The only matrix that satisfies this equation here are type of matrices J of the form up to some constant or normalization of Hadamard matrix dimension 2.
Wait, why do you want the equality?
Sorry?
Why do you want equal to 1?
Oh, because in the CHSH game satisfies this, and you want to see whether if there are other games that saturate the inequality, so it equals to 1.
Does it imply something that it's equal to 1?
Sorry?
What do you know about the game when this is equal to 1?
No. What we want to know, which class of games, what are the form of the games that gives you the equality with 1.
But why?
Because we want it like the CHSH one, the CHSH game.
It might be just a property of this game, like it's not related to locality. To locality or anything. I don't understand why it is important this equal to 1.
Because
I understand that CHSH satisfies it, but what do you know about in general?
Because if you go from n strictly larger than 2, strictly larger than n from 3 to number n, so you will not have an inequality here. Yes, and you want the equality also.
Okay, I don't understand why you want the equality, but okay, I can ask you later.
Okay, sure.
But what's the goal? You want to find something where incompatibility implies a Bell violation of a corresponding inequality. That kind of what you're looking for in the end? That's why you want this equality?
Yes.
Well, that's a key point, I understand, by generalizing this result.
See the equivalence between the.
Right, but as you said, one direction is clear, right? That compatibility implies there's no Bell violation, right?
Yes.
So what you have to see is if what you want to kind of establish using these bounds and maybe something else is that if C is larger than 1, right, which means incompatible, I understand.
Yes, exactly.
The C norm, then the G norm must be larger than beta or something like that, right? And this should boil down to this condition you write, I guess, right?
Yes, exactly.
Can one see how this boils down to that condition? I just tried and I failed.
Yeah, I don't see how.
Because that seems to be the key of the whole point, so I think maybe we should actually clarify it.
How do you arrive to the conclusion that what you want is this condition max times beta equals 1? Easy.
So we want, so in general we can show this. Okay. And if n is greater than 3, so this inequality is strictly larger than 1. So we have just the strict inequality. And if you want the equality also to hold, maybe I'm not.
No, maybe we can talk about it.
Yeah, but if you have equality between this, so if this expression is 1, it means that you have incompatibility equals non-locality. Is this the statement?
So the statement is that yes, which type of games those are. This type of the equality here will characterize completely the games that gives you the equality between the two norms.
I want to see this. I mean, I wrote something, and what I wrote, but probably I made a mistake, is that whenever beta times this maximum is larger than 1, you will get a violation of 1 if you have a violation of the other, which seems too strong, but
You can.
we can discuss it afterwards, but my feeling is that that's the essence of the talk somehow, right? Maybe I'm missing it, but that's my feeling, that that's what the whole thing is about, right? Generalizing this result.
So the thing is that if you want the equivalence between these two norms in this sense, so all what you will have, so it's to satisfy an inequality, and if the inequality is strict, so you want this inequality not to be just strict, but also to satisfy the equality with 1, and equality with 1 holds only for those type of games like CHSH game.
Okay, so you want equality of the norms, which is a much stronger statement than what you wrote there, right? Somehow. This is just saying if one is bigger than 1, the other one is bigger than beta.
Yeah, but
Which is not saying that they're the same norm up to a scaling. They're just saying at a specific point they're the same up to a scaling, which is much weaker. But you want something stronger.
yes.
Okay. Okay.
And the thing is that so the equivalence there in the paper traduces here with the equality, and if you want this equality to hold, so you have this inequality, and if you want the equality with 1 here, you should see the type of matrices that gives you this, and those are type of matrices that gives you the CHSH game. Up to some scaling, up to some normalization. It's not really important.
Sorry, the implication incompatibility implies a violation does not imply the equivalence of the norms, or it implies the equivalence of the norms if beta is 1.
Yes.
Okay. And you're okay.
Yeah, this is.
So you're considering beta equals 1.
And this is also we wanted a condition like the CHSH game. If there exists a beta that gives you this. Okay, so I think I will stop here. So one last thing. So in all these settings, so what we showed, so we have these two norms that will characterize incompatibility or will characterize non-locality, and the only games that gives you the equality between these two norms are type of the CHSH game, and in all this setting, Alice and Bob's answer are just plus and minus 1. Can we generalize this setting for more answers? Does this norm, compatibility norm, holds also, or have this nice formula there for more than 2 answers setting? So we don't how we can generalize it, yes, and maybe also we can ask how much entangled states that can be shared between Alice and Bob to see whether how much is violating the, or do we have the how much this equivalent between these two norms holds, etc. So I think I will in that here.
Okay.